Morning, everybody. It is our pleasure, together with my friend and colleague Stefano Tebaldini, to welcome you to this lecture on polarimetric SAR tomography. Polarimetric SAR tomography is a very wide subject, so in a few hours we will not have time to go into the details and explain you all the tricks and the different strategies you can use to perform polarimetric SAR tomography processing. But instead, we will try to give you a taste of what you can do and to give you the basic principles behind this kind of way of processing SAR data in order to analyze remote environments. We will go through a set of lectures. I will start with an introduction and I will show you later on the structure of the lecture, but we will mainly alternate between Stefano and me. Stefano will give you some insights on the 3D SAR imaging, and I will go more on the signal processing side. He will show applications, and at the end, we'll do a practical this afternoon together with Professor Potier on using Pol-TomoSAR Pro and showing you that at least with this software you can perform the very basic steps of SAR tomography. So let's start. Oh. Okay. So during this introduction, I will. The aim of this introduction is to make the link between what was presented yesterday by Irena Hansek. She mainly spoke about Pol-InSAR, but I know that I attended a lecture some time ago. I know that she also talked about tomography, so that's good. Makes a smooth transition to our lecture. So we'll go from InSAR and Pol-InSAR to Pol-TomoSAR. To do this, we will use the well-recognized random volume of a ground model. That makes a perfect link between these two ways of processing data. And at the end, I will give you the structure of the processing. So when you look for tomography on the internet, you cannot miss the major contribution by Kak and Slaney, which was written a long time ago in '87, and they wrote a book that you can read for free because it is open and fully available. It's called Principles of Computerized Tomography. It's a very wide book on tomography, not only in what's our kind of tomography, but in many different kinds. And they, in the introduction of their book, they summarize tomography using the following sentence. They say, fundamentally, tomographic imaging deals with reconstructing an image from its projections. It's a very basic definition, but it's very right at the end. So I gave you here some examples of projections you can use to reconstruct an object. On the left, you have two cylinders seen from the top. And here, along these two lines, you can see the projection of these two cylinders. Here, the distance of this line is the maximum distance between this axis and the part of the space, which is covered by something which is not the air, which is in this case cylinders. So this distance here corresponds to the orthogonal distance between this line and the last point you can see there. And you see, when you look at these two projections, you really, from this one, you could not say that you are looking at two cylinders. But when you add to this projection this other one, then the whole scheme, the whole picture starts to be much more clear. So this is a nice example of what tomography is about. You have different projections because you cannot perform 3D imaging at once. So you use either 1 or 2D projections, and from this projection, you try to guess what you were measuring. And this is an inverse problem, which has solutions that are more or less simple. On the right-hand side, you have a very famous application of tomography, which is specific to the case when you deal with a non-diffracting case. Means you are emitting waves from locations here using specific emitters. The wave propagates along parallel paths here, and when they go through a medium you want to analyze, you want to characterize, these waves undergo an attenuation. And what you can measure, you cannot measure the extent of this volume, of course, this is what you want to know, but you can measure the wave attenuation for a given orientation of your emitting and receiving system. this way of performing tomography is called non-diffracting tomography, because the interaction between the wave and the volume does not modify the wave propagation. It only affects the amplitude of the signal you receive. And if you perform projections along different theta, you may show easily, and this is what is done in the book by Jack and Sliney, you can reconstruct the object. Why? Because it is possible to show that when you have this kind of profile, which results from the measurement of the wave along this axis here, if you take the Fourier transform of this profile, then you, in fact, you are measuring the spectrum of the object along a given line in the 2D spectral domain. So this is called the Fourier slice theorem. We're not going to study this, but it's just to show you that it is, in fact, very easy from this projection to make Fourier transform, and you measure the object from along this line. In fact, you measure several lines, as this is indicated here. And how do you perform focusing? You just make an inverse 2D transform. This is the major tool that radar engineers like to use. So in our case, we're not in this simplified case. We deal with diffracting media. So we apply diffraction tomography. Why diffraction? Because when you use a radar and you emit a wave toward an environment, the direction of propagation of this wave is modified by the environment. This is why we call it diffraction tomography. This is a coherent processing. You need to pay attention to the phase of the signal, or to the delays of the signals. You don't only deal with amplitudes, you also pay a lot of attention to the shape of the signal you receive and to the way they are delayed from one from the other. And in fact, if you want to make things simple, tomography, the way we think it, is a generalization of interferometric SAR processing using a synthetic array. You don't use only 2 images, but you use more than 2 images, let's say 2, 10. The larger, the better in terms of resolution. So in order to understand what I mean with array, I gave you an illustration here. On the left-hand side, you have a way people used to represent the Pol-TomoSAR mode that will be adopted by the future biomass mission. You may have heard of this mission during this week. It will be launched in 2023, and it will measure the terrestrial environment from space using a P-band SAR device, and by combining the data acquired over different orbits and putting all these images together, you can describe an array in this direction, an array of sensors. Why is this possible? Because P-band corresponds to very large wavelengths, and for this wavelength, the environment can be considered to remain coherent over the whole acquisition time. And if you combine 6 or 7 images of these along different trajectories, you may be able to perform 3D imaging. This is the objective of tomography. How do you do so? But on this drawing here, on this schematic, the different acquisitions are represented under the synthetic form of an equivalent array, where you have the first acquisition, the second, the third, the fourth, the fifth. Okay. And here we represent what Stefano will take a lot of time to present after, the principle of tomography, when you perform SAR imaging, radar measurement, sorry. The only thing radar can measure is a delay. Okay, it sends the signals, receive a signal, and say, oh, there have been some time between the moment at which I emitted an echo and I received the response of the environment, and knowing the velocity at which wave propagate, you can deduce the distance between the sensor and the objects. So if you measure a distance, in this case, from this point, you will, if you have a given resolution in range, you will be able to measure the distance of all the points belonging to this resolution cell here. And this is extremely good because you can localize environments. But in our case, in the case of volumetric media, this is not that good, because using this kind of processing, you will not be able to differentiate the response of the tree canopy here and the ground, because they are located exactly at the same distance. And using array processing, as Stefano will show you, you are able to further discriminate this resolution cell into more refined 3D resolution cells here, and you will be able to say, okay, in this one I have the response of the canopy, in this one I have the response of the ground, maybe single and double bounce reflection on the ground and the trunk, and then you would use POLSAR Pro and polarimetric processing in order to analyze, to try to separate single and double bounce. Very quickly, some illustration of what you can do with tomography. Let's say that with these different acquisitions of the biomass sensor, you measure this image, which is part of the Parakou test site that has been imaged by the Onera AMSES sensor in the frame of the TomoSAR campaign, which has been planned by the European Space Agency. So when you look at this image, what you get here, the reflectivity is more or less related to the presence or not of forest and to the underlying ground topography. And because when the range slope varies, you have huge variations of reflectivity. So it's very hard to infer tree height or biomass content using only one image. People aim to do this, but you need to do a lot of compensation. You need to know the topography of the scene. Instead, if you just combine 6 images quite in a specific configuration, in the multi-baseline interferometric configuration, and if you apply tomography processing, you are able to get this kind of drawing, which is a tomogram. Here you see the response of the ground below the forest, the top of the forest, and everything is very clear. You just apply the equation from the book, and you get this very clear answer from this kind of tomogram. You can try to separate the ground contribution from the volume, and you get very, very good estimates of the underlying ground topography and tree height, which are comparable, not the same quality, but comparable to LiDAR measurements. You get information, you can see it. Here we compare LiDAR with TomoSAR. From a very large distance, you cannot really make the difference between these two estimates. Of course, there are some differences. We don't have the same resolution. Okay, so how to go from InSAR and Pol-InSAR to tomography? We can try to do it very quickly. Irina might have presented the basic configuration which motivated the use of polarimetric SAR interferometry. Let's consider a volume, it's in a forest with the ground here. You have forest with trunks and tree canopies. As radar engineers, we don't like to look at forests. We like to look at media with given propagation conditions and given extent. So we just idealize this forest under this form. Here you have a ground. You may have trunks and a canopy, and this is even not enough. Idealized for us, we just want to convert this in terms of reflectivity. We know we will have a response from the ground, a response on the canopy, and in fact, when we look at a volume, we like to consider a volume according to the way it reflects waves as a function of height. This is the FZ, is the ultimate objective of tomography reconstruction. This is what we want to estimate. How do we do so? You can do it by doing interferometric processing. Why? Because it is possible to show, but we are not going to do it today, that the interferometric coherence, once you have compensated for many sources of perturbation, you may isolate one term here in the interferometric coherence, which is called the volume vertical decorrelation factor, which is tightly linked to the way the reflectivity of the volume you are looking at spreads in elevation. So you have this very famous equation. We are going to give examples of values of coherence you can get depending on the vertical spread of the medium reflectivity. So here the main factors are this function of Z, which is the vertical structure of the volume. Here the KZ, which depend on the interferometry baseline, the wavelength, the range distance, and the main incidence angle, the mean incidence angle of the pixel you are looking at. And of course, it is a normalized, the modulus of the interferometry coherence lies between 0 and 1, so it is a normalized indication. When you show this to electrical engineers or to radar engineer, what they see here is a Fourier transform. This has exactly the shape of a Fourier transform. So we can say that the relationship between the vertical structure of a volume, once you have identified, of course, and you have isolated the part which depends only on elevation, the relationship between this reflectivity profile and the interferometric coherence is a Fourier transform. The nice thing with the Fourier transform is that you are able somehow to invert it. Every time you go from one domain to the other using a Fourier transform, you can apply inverse Fourier transform, means that there is a processing which will help you to estimate this vertical reflectivity function from interferometric coherences. And let's investigate how this works. So in order to do it, we just try to represent, to see how to represent a natural volume. So if you go into now very old books, you can find a way to model the reflectivity of random volume and random environments using the so-called radiative transfer theory, which is based on the resolution of the differential equation. This is not very important. What is important is that at order 1, you find that the response of a volume is given by a sum of, in this case, 5 contributions. Reflection from the top, reflection from the ground after propagation through the volume, reflection from the particles inside the volume, and you have some double bounce reflections here and triple bounce on the ground back to for the particle and back to the radar. If you go to modeling at order 2, you will have many more terms, but already in this case, you can show that in many environments, not all of them, but in many environments, this number of scattering mechanisms can be reduced to a much lower one because of you can neglect some terms. So the amplitude is very low. For instance, this triple bounce scattering mechanism is very often neglected. Not always. In some cases, it can be present, but in most of the time, it is the amplitude is very low, so we can neglect it. And as we will show later, direct scattering from the ground and double bounce scattering between the ground and the particle inside the volume, these two scattering mechanisms cannot be separated using SAR imaging. They have different responses, but they always fall exactly at the same position. So in this case, it's not worth to use two terms in order to represent them, and you can just represent both of them using a single scattering mechanism. Over forested areas, the interpretation we have in terms of single, double bounce and propagation is slightly different. Of course, we have a low density medium, so we have no refraction. You may have refraction when you look at ice or snow, not forest. And basically, if you go back here, you see that at the end, here we may have a reflection from the canopy top, but this reflection will not be very strong. If it is strong, you can even merge this contribution and the volume and say this is all of this is coming from the top part of the volume. So you have two contributions, one from the ground and one from the, and these two are of course uncorrelated. There is no specific relationship. So we have two contributions, and now we are going to see how interferometric coherence varies when you put the one or the other or both contributions together, and this will lead us to the formalism of tomographic focusing. So here I use this relationship between the vertical structure and the interferometric coherence, and I consider only the ground contributions. We have only one ground. The reflectivity of this environment can be represented only using only a Dirac pulse here with a given amplitude, which is called sigma j, which is the reflectivity of the ground. And when I inject this expression inside this integral here, I end up with this very simple expression. The interferometric coherence has a modulus equal to 1, and the phase is directly related to the elevation of the ground. So this shows us why InSAR is so well adapted to topographic estimation. Perfect. So now we go to another kind of response, where you have a strange medium. You have a volume flying in the air. You have no ground. Okay, it doesn't touch the ground, and you have no response from the ground, so it just flies. Why do we do so? Because we want to analyze both contributions separately, and after we will merge them, because everything becomes a bit more complex when you consider both ground. So let's say we have a volume which lies between two coordinates in elevation, and it has then a width. And this volume is particular, again, it's idealized. We have no extension. So the wave propagates through the volume without being attenuated, and but we have some scattering. Okay, it's kind of a strange volume, but it is a first step in the description of natural environments. Later, we will incorporate extension in our analysis, and when you do this, you just insert this kind of volume reflectivity in elevation into this integral here. You perform the integration, and you end up with a very Irena talked about this yesterday, I'm sure. You end up with a very well-known shape for the interferometric coherence, which is made of two terms. The phase term gives you the volume center height, because you have the mean elevation between the top of the volume and the bottom of the volume. Here, this is the top, it's the bottom. And the sink here, the amplitude of this cardinal sign here is proportional, is a function of the width of the volume. So you have the main elevation of the volume, here the width. Means that you have everything you need to characterize the volume. So InSAR is well adapted to volume analysis under specific conditions. The conditions in this case is that you have a null extension, the wave propagating through the volume without being significantly affected in terms of amplitude. In this case, the measurement of the coherence and the phase and amplitude of the coherence can help you to fully characterize the volume. Okay, at least if this is, of course, this is idealized, but it shows you that coherence is a nice tool to, decorrelation is a function of the presence of the volume, and the phase center, okay, the elevation which corresponds to this phase term here, it gives you an indication of the position of the volume in space. Now let's go to a slightly more complex situation where you don't have any more a non-attenuating medium, but your medium attenuates and has a constant extension. Extension is the concept which is summarized here. When you propagate along a given direction here, you say that the loss in intensity between this point here is proportional to a factor which is called the extinction, of course, to the original intensity at when you enter the volume, and to the length of this path here. Okay, so the larger the original intensity, the larger the losses, which is something we can understand easily, and the longer the path here, the longer the larger the losses. And this is a differential equation. When you solve it, you end up with a shape for the reflectivity, which has an exponential shape, which is an exponential function. So when you consider a constant extinction, you end up with this exponential-like reflectivity distribution in elevation. Of course, if you want to calculate the total intensity scattered by the volume, you just need to integrate this function, and you get the intensity. And the nice thing is what happens when you insert this into the expression of the coherence. You end up with a two-term. It starts to be a little bit harder to analyze, okay, to analyze the analytical expression. Instead, here I plotted some examples of decorrelation for extreme values of extinction. Here you have a given baseline. Okay? Well, here you have the x-axis represent the height of the volume, the width, in fact, because we consider that the bottom is on the ground. Z equals 0, and this is the decorrelation you have according to the function of the height for different values of extinction. You see that when the extinction is equal to 0, we end up with the sink shape we had before. It's exactly where here, this sink shape. But when the extinction becomes larger, this cardinal sign shape it's modified, and we start to have a kind of increase of the curve, which tends toward a flat response in this domain. So why do we have this? Simply because when the extinction here is extremely large, you have the reflectivity, which is characterized by a peak here, and a sudden decrease to zero. The waves are attenuated. In this case, the waves cannot penetrate inside the volume, and the volume starts to behave as a surface. And you end up with the classical interferometric response of the surfaces. So with a decorrelation, a null decorrelation, we have the coherence whose modulus is equal to 1. So the physics are preserved, everything's going well. We can have a coherent explanation for what's happening. So in this case, if you want to characterize, to estimate the depth of the volume using only the modulus of the coherence, you end up with an ambiguous estimation. Of course, you don't know in which case you are. If you have a decorrelation, let's say 0.65, you don't know if you are looking at this kind of response or this one, and you may have a different depth values. If you look at the phase also, you have the same phenomenon. You have when the extinction tends towards zero, you have this relationship. Your phase is exactly the middle of the volume, and when the extinction is very large, your phase center goes toward the top of the volume, and you have a surface-like behavior. And you don't really know where you are between these two cases. But I think that if you know you have an exponential shape reflectivity, using both the amplitude and phase of the coherence helps you to estimate its vertical extent. But you need to know that you have an exponential shape. And last but not least, the random volume of a ground model with both volume, attenuating volume, and ground. You merge everything together. So now the reflectivity profile is a Dirac on the ground and an exponential for the volume. And if you want to compute the intensity by scattered by the volume and by the ground, you just apply these expressions here. Here, please note that you need to account for when you compute the ground intensity for the two-way propagations through the volume. The way it is attenuated, that will go through the volume on the way down, and this is why you have this exponential term. When you insert this inside the expression of the coherence, you end up with this final expression, which has two terms. The first one is related to the volume. Okay, this is what you would get if you had a null ground response. And the second term is related to the ground. This is what you would get if you had no volume. And depending on the relative amplitude of the relative value of the intensity by scattered by the ground by the volume, you have this M factor here, which is called the ground to volume intensity ratio, which lies between 0 and plus infinity. And according to the value of this factor, you end up with a different interferometric coherence. So you may have an interpretation. When M tends towards 0, of course, you have the ground response, which is close to 0. So you're looking at the volume, and you may apply your favorite volume characterization technique. But remember, you need to know the exponential shape. You need to be sure that the volume has a constant extinction. And when M tends toward infinity, it means you have a null for your response. In this case, you're looking at the ground, the coherence of the volume of the interferometric coherence as a unitary modulus, and the phase gives you the elevation of the ground. Basically, you cannot solve this problem if you don't know ratio of these two intensities. So this is why Shane Cloud and Constance Papathanassiou in the beginning of 20 years ago, more than 20 years ago, decided to use polarization as another source of diversity in order to try to solve this problem. What they did, what they had in mind was to, when you look at the environment, is to fit the polarization, try to find the polarization which brings you the phase center here closer to the ground. Why? Because we know that the ground and volume do not have the same response. This is what we saw with the hypothesis. So if you have a polarization which is close to the one on the ground, you expect to see mainly to have a very strong intensity from the ground and small one from the volume, and then your phase center will be here, and you can estimate the height of the ground. And when you find another polarization, then you orthogonal to this one, you expect that you have a response from the ground which is close to zero, everything comes from the volume, and then you can analyze the volume the way you like. This is what would happen in a perfect world, but we know that radar, everything is somehow random and not as perfect as we would like to. And in fact, when we will see on tomograms, 2 minutes, that's actually, there is no such polarization that you can see that allows you to see only the ground or only the volume. It's, life is a little bit more complex than what we would expect, but this effect of obtained by combining interferometric diversity and polarimetric diversity is present, and this is what Shane and Costas used to first to investigate how to use this diversity in order to further characterize the volume. So how to model this? It's simple, and the main equation, the main expression you have to remember is this one. The reflectivity of the volume, okay, is a function of polarization, of course, and a function of course of space. Okay. So this expression F, which is a function of Z here, and these two expressions can be separated. And this is the main hypothesis behind this modeling. You can separate polarimetric and spatial effect. This means that the extension is not a function of polarization. This F here comes directly from the Fourier transform of from the exponential shape we have when we assume a constant extension here. And this is not a function of polarization. If this is true, then what I'm going to say in the next slide is okay, and you can well analyze your volume. Okay, so we have a response from the volume, which is function of polarization, of course, but not the extension, and the response of the ground, of course, is a function of polarization. So we integrate these terms in order to get the intensity, so no surprise, okay, compared to what we had before. And the main result is represented here. The correlation of the volume is not a function of polarization, because you can factorize the part which is related to polarization from the part which is related to space. And when you do this ratio here, these two terms vanish, and you end up with a volume which is exactly the same, whatever the polarization. And of course, the ratio of the intensities from the ground and from the volume is a function of polarization, and this is what you want to use. So you want to look for a polarization for which the response of the ground is equal to 0. We know that this is plausible. There might be situations for which you can find such a configuration, and let's say for the ground, you learned with Eric that when you use the HV polarization, you look at the surfaces, very often the response in this channel is extremely small. And when you look at volume, of course, it is very large. So this could be a solution. And if you want to have only response from the ground, and in this case, you would like to find a polarization for which the volume has a very weak response, and you know that this is very unlikely. So how to solve this problem? Then you need to use a line. I'm not going into the details here, but you need to use a line presented by Shane and Costas. This is what you get when you vary the polarization over the whole space, and they propose to extrapolate this line toward this intersection between the line and the unitary circle, because they know that over the ground, if you had no volume, you would have a coherence with the volume is equal to 1, and this gives you the elevation of the ground. And on the other hand, here they hope that for this polarization, the response of the ground is very small, and that you can characterize volume using your favorite assumption. Not just needed an assumption to do it. What about tomography? Tomography proposes another solution. Instead of using a single baseline, you want to use, let's say, n different baselines. And what do you get? You get different vertical wave numbers, and for these different vertical wave numbers, you measure each time a coherence. And when you compare the values you got on different baselines, in fact, you can, with this example, you can really, only for the modulus, in this case, you can differentiate these different extinction profiles, correlation profiles here. And you will know very easily using a few sampled values on which curve you lie. So this sampling gives you an asymmetry. You know the shape of the extinction profile, which is exponential in what I said before. You may even, if this kind of information is very rich, in fact, you may even want to leave the classical constant extinction hypothesis and to try to characterize the volume without any assumption on the vertical profile. This is what we call non-parametric analysis. You just know you're looking at the volume and you want to get it. And you may even want to complement this analysis by including, of course, polarimetric diversity. One example, here are tomograms obtained over the Krickland test site at Elband. Krickland is a forest located in Sweden. These data were acquired by the DLR in the frame of the BioSAR 2 campaign. And here you have profile obtained for HH, HV, and VV. What it will do, we just represented here this tomography profile, and we superimpose the phase center height we get by considering the different couples of SAR images. I mean, this is an interferometric information. You have here the phase difference between the master and the second image, and the master and the last image. Okay. So here you start from the first couple, first interferometric couple, to the last interferometric pair. And every time we paid attention, the phases are not right, and you can convert easily a phase into height using the vertical wave number. And when you look to this with more in detail, this is the first pair and this is the last pair. Here you have a small baseline, here you have a large baseline. And what you see that when the baseline is too small, okay, whatever the polarization, your phase center is located around the treetop because you don't intercorrelate enough. In this case, the gamma volume is, in the sink shape, you are really at the top of the sink, and you whatever the polarization, you cannot decorrelate enough so that the correlation from the ground becomes dominant. And when you use the larger baselines, but we are in an airborne configuration, so at the near range the baselines are very large, and far range they are much smaller. And you see that there is a given domain of baseline, of orthogonal baseline of KZ, for which you have phase diversity. And when you have phase diversity, it means that you can playing on polarization gives you full range of variation of the coherence. If you stay here at the top, at the near range, you will see all the phase centers will be on the ground because the volume decorrelates too much. You cannot find a polarization for which the center is high in the air or high in the volume, and the opposite at the here, when the baseline is too small, in fact, you cannot find polarization for which the ground becomes dominant in terms of correlation. So you need to choose carefully your KZ value. And this is what was published by our colleagues from DLR some time ago. They didn't use this tomographic analysis, but they say basically the same thing. And the nice thing is that when you do tomography, in fact, you just use jointly all this information, all the things you don't choose. And whatever the baseline here, you are more or less able to see that you have phase diversity. There are some parts of some images for which you would be on the ground, other for which you would be at the treetop, but more or less for all the polarization, you would be able to reconstruct a tomographic profile without any assumption. And this is what makes tomography very interesting. As you will see and I'm going to give soon the floor to Stefano. When you do tomographic processing, you have two ways of doing mainly. The objective, of course, is to transform a range resolution cell into something more useful, where you discriminate scatterers according to their position in a cross-range direction that we convert after a while into elevation. And there are two ways to do this. The most general one is direct 3D imaging, but it is also very complex. And most of the time, when you get data from agencies, from GLR, from ONERA, you don't have the information, enough information to perform this kind of processing, unless you can guess parameters and you can retrieve them, but you need to have a lot of experience to do this. But this is really the most robust way to do it. And under some simplifying assumptions, I will detail slightly more than 1 hour. You can transform this problem into a much more simple spectral analysis configuration, where instead of really trying to retrieve the full 3D information, you just try to combine as well as possible several 2D images in order to recreate a volume. So some examples, I'll go very quickly. This is a fantastic result found by Stefano and his colleagues some years ago of a glacier in the Alps, and you see that using several tracks, he was able to map the reflectivity inside a glacier in the Alps. And here you have images, polarimetric images obtained at different rates. In order to do this, of course, in this case, the depth you're looking at is so large that you cannot use simply simplifying assumptions, and you need to perform full 3D imaging. But in other configurations, which are much more simple, like the one I showed before using the BioSAR campaign, you can, using simple spectral analysis techniques, you can map the reflectivity of a forest. This is a boreal forest. These are phase reflectivity and the depth, and you can map easily what happened on the ground and what happened in the different. You can separate different layers within the forest canopy. What I showed before, this is the tomography obtained of a tropical forest, and you see that at all polarizations, we have more or less response from the ground. So, and from the treetop, and you are able to follow by the way, what is represented in black here are the LiDAR profiles. So you see that we're close to the visual information which are going to LiDAR. And you can also use tomography for urban areas reconstruction. So the outline of the course is the following. I have finished now with the introduction. I let you with Stefano, who will show you the principle of 3D SAR imaging. Then I will come back to present you spectral analysis techniques, how you can use methods that are analog to discrete Fourier transform in order to recreate your volume. And then we will have a lunch break, I think. And in the afternoon, Stefano will present you some campaigns, results, and also the SAR SIM toolbox we have been preparing some years ago, and you should have the possibility to download on your own PC. And this afternoon, I will come back and make the practical support together with the project. So I don't know if we have some questions, maybe not. I have been a bit long, but this year I wanted to take a bit more time for the subject, currently the subject, and maybe I will go a bit faster after a while on the mathematical details that you, in fact, you will have the possibility to read once you're at home. I don't know if you have any questions. Basically, I just introduced the concept, so if you have specific questions, you might have the possibility to ask.